Let's get started. Today we have Jerry Lee from MSR, and he'll be telling us about nearly optimal algorithms for robust mean estimation.
Okay, cool. Yeah, thanks. So yeah, this is joint work with Sam Hopkins. So let me tell you about the problem first of robust mean estimation. It's a very simple to state problem. I have a distribution over RD, and it has mean mu. Okay, and I get samples x1 through xn from this distribution D. But an epsilon fraction of them are corrupted, where I think of epsilon as a relatively small constant. And by corrupted, I mean like completely arbitrarily corrupted. And I'll show you a picture of this in a second. So I'm not going to impose any constraints on what happens on these corrupted points, except that there's an epsilon fraction of them. Okay? And the goal is now I get this corrupted set of samples, and my job is to recover some mu hat, which is close to the true mean. In this talk, I'm going to focus mostly on L2 distance. Okay? But you can consider other problems as well, but of course this is sort of, in my view, at least the most natural. For most cases. Does the problem make sense at a high level? So as stated, this problem is impossible. I'm going to need some assumptions on my distribution D, because then like if I don't, then how can I distinguish between just a weird looking distribution and a corrupted distribution? But I'll get to these assumptions later. And it turns out you can get away with relatively mild assumptions. So the picture is something like this. I have a nice distribution over my uncorrupted samples. And then I give this distribution to somebody I really dislike and who really dislikes, me. Well, really doesn't know me, but a bad person who is very powerful though. Usually I try to appease the crowd, but somehow when I'm in New England or Pittsburgh, I can't resist. But I give it to a bad person, and what he's going to do is Roethlisberger is going to look at my distribution and corrupt an epsilon fraction of these samples in any way he wants. Like so. So he's going to do this, and then I get this set of samples, and without the colors, obviously. And now my goal is, given this corrupted set of samples, recover the mean. And I want to emphasize that these red points could have been moved anywhere. They could have been moved arbitrarily far or whatever. Yeah.
I forget. Can the corruptions depend on what the rest of the realization of the other points?
Yeah. So the full setting that we're going to assume turns out doesn't turn out to be much of a difference, but is first. The adversary can look at all the samples and then choose some fraction to corrupt. Yeah, so there's a relatively strong notion of adversary. Okay, so before I tell you about how to solve this problem, let me explain a little bit why. Oh, sorry. And a piece of terminology, let me call a set of samples generate this form, epsilon corrupted. This is just a short way to describe this process. So hopefully this process makes sense. So the formal mathematical question is, given an epsilon corrupted set of samples, recover the mean from the distribution. Okay? Okay, so why do we care about this problem? Well, first of all, it's a very natural, very fundamental question, I think, from robust statistics. It predates even modern machine learning, going back to work of statisticians from the 60s and 70s. And it has a lot of nice statistical interpretations as well. And also more recently, it's found many applications in practice, in the sort of development of reliable machine learning systems. So here's a incomplete list of things. And as sort of theoretical point of view, it's in some sense the most basic robust primitive in this setting of learning in the presence of outliers. And it turns out that a lot of problems can either be black box reduced to this problem of robust mean estimation, or you can kind of use the same techniques to solve these more complicated problems as well. Okay, so that's why we care about the problem. So now what was known? So surprisingly, despite the fact that it's been studied so much, for a long time, these algorithms developed, these classical algorithms, they were either inefficient in high dimensions, namely they ran in time which is exponential in the dimensionality of the data, or worse, or they lost factors in the error guarantees which are polynomial in dimension. Okay? So either I just couldn't run my estimators in high dimensions, or I could run my estimator, but then I would get some garbage when dimensionality was couple thousand, which is relatively small nowadays. Okay? So there's a very natural question of is this even possible in high dimensions at all? And it turns out recently, I guess 2 years ago, in some simultaneous work by Live Robin Paula and by Deek, Nicholas, Kamath, Kane, myself, Ankur Moitra, and Alistair Stewart, it turns out you can actually get around this. So you can get efficient algorithms that don't lose any of these poly D factors. So you can get robust estimation in high dimensions. And this was pretty recent. But in these original works, these are really theory works, we focused on efficient being polytime. Okay, so the question that we're going to focus on in this talk is really, how efficient can we get these algorithms to be? Okay, so here's a sort of rundown of what was known for these efficient algorithms that got this these nearly optimal errors. So we're going to have 3 parameters. First, n is going to be the number of samples, d is the dimension, and epsilon is going to be the fraction of corrupted data. Okay, and I'm going to be focusing on algorithms that get sort of this nearly optimal error guarantee. I haven't told you what the concrete setting is, but just trust me that this is generally seems to hold amongst a number of interesting settings. Okay, so the first algorithm that we kind of presented is this very convex programming based algorithm, and I was too lazy to actually work out what the poly is, but it's some pretty bad poly, because it turns out that you actually fundamentally require running the ellipsoid algorithm. So somehow that's going to be quite slow when the dimensionality is high. But I mean, it's poly time, so that's good from a purely theoretical point of view. In the same paper, and in the paper by Lyra and Paula, there were 2 algorithms that actually got relatively better. I'm going to not focus on this one because it has some caveats I don't want to get into, but oh, there's typos there. Oh, whatever. Yeah, so this iterative filtering algorithm, it gets runtime which is O tilde of nd squared, which is pretty good, right? Because if I have n points in d dimensions, then it already takes nd time to read all the data. So that would be nearly linear time. So this requires d passes through the data. But when d is kind of large, this can be a little bit problematic, right? When d, this is a lot of passes through the data, when d is 1,000 or tens of thousands or whatever. So, it's not bad, but it's not optimal. Very interestingly, there was a paper in this year's SOTA by Cheng, Dick, Nicholas that showed a very interesting runtime of O tilde of nd over epsilon to the 6. Okay, so when epsilon is relatively large, this is the right answer. Nd is the best you can ever hope for. That's how long it takes to read the samples again. But it gets this nd over epsilon to the 6, which is bad for 2 reasons. One is this is a big number. 6 is pretty large. So when epsilon's 0.1, this is a factor of a million, whatever. And the second issue is a more qualitative issue, which is this, that when the fraction of corrupted data is getting smaller and smaller, it should not be the case that my runtime gets worse. That just doesn't qualitatively make sense. The problem should get easier and easier, right, for the fixed number of samples. And somehow if I understand correctly, the reductions here fundamentally require more and more runtime, which is bizarre. But yeah.
At some point, as epsilon gets big, then the end doesn't exist, right?
Yeah, that's a good point. So there's a notion of breakdown point as well. So which is right. So for instance, when epsilon is greater than 1/2, at least stated this way, it's impossible to do anything because there's more bad points than good points. So how could I possibly ever distinguish?
Drilling down like Valiant does. Or something.
Right. So you can do things like this list learning kinds of things. In this talk, I'm going to focus on the regime where epsilon is relatively small. It's actually an interesting question of what the breakdown points of. So breakdown point is what's the largest fraction of epsilon for any estimator where the estimator continues to produce consistent answers. It's actually a very interesting question of what's the best breakdown point for efficient algorithms. So it doesn't seem to be 1/2 currently, at least. It's kind of interesting. It's more like 1/4, but yeah.
Is it clear that you need n there? If n is very large, do you need to read all the points?
Yeah, that's a good point. So we're going to typically focus on the regime where n is either below the threshold at which you would need to get the information theoretic limit, or at that threshold. But it is true that you can subsample when n is sufficiently large. But I'm just going to, yeah, that's a good point. Okay. So in this work, we're going to give a new algorithm that gets the right answer. So it's going to be completely ND. So no epsilons or anything like this. It's just polylogs off. Okay? So that's what I'm going to be talking about. Okay? So let me give you a formal statement of our results, because as stated, I still haven't told you what the problem is, because I haven't told you what assumptions I'm making on the data. Because I need some, as I mentioned before, regularity conditions on my data, otherwise the problem is ill-defined. And it turns out that you can do this in a number of settings. I'm going to focus on one which is under which I impose relatively mild conditions, where I'm just going to assume that the covariance of the true distribution is bounded or exists. So and by some scaling, I'm just going to assume that the true covariance has largest eigenvalue at most 1. Okay, so here's our theorem. You get epsilon corrupted set of samples, x1 through xn, from a distribution D, where this distribution has mean mu and covariance sigma. And again, sigma has It's PSD bounded by the identity, which just means that its top eigenvalue is at most 1. Then there's an algorithm which achieves the following error rate. I'll parse that in a second, and the algorithm runs in time, which is nearly linear. Okay, so let me parse this error rate for a second. The second term, this root d over n, is unavoidable even without like corruptions, up to this O tilde. So that's just like the rate I pay for like convergence of the uncorrupted samples. And it turns out the first term, this root epsilon, is unavoidable in the presence of like corruptions. If I have epsilon corrupted samples in this distribution with these assumptions, there's no estimator, no matter how many samples, no matter how much runtime, that can ever get error better than root epsilon. You can prove this. Okay, so this is sort of getting the right answer in terms of both of these parameters. And as Raj pointed out, in particular, when like n is sufficiently large so that this quantity is bigger than root epsilon, there's no meaning in taking that many samples, so I might as well subselect. But for simplicity, we're going to focus really on this regime, which is sort of the critical regime anyways, which is when n is roughly d over epsilon, in which case this term is equal to that term. Okay, and this is just for simplicity. It turns out you can do everything more generally. But in this case, then we're going to get O of root epsilon error for everything. Okay? But you can do the more general cases just like bookkeeping in general. Yeah.
I missed the first couple minutes of your talk. So
Sure.
What is the algorithm finding?
Right.
You have a sample that's been epsilon corrupted, which means a fraction of epsilon that has been corrupted. Is that what that
Yeah. That means just the epsilon fraction of the points have been arbitrarily changed.
arbitrarily changed any value?
Any values.
Okay.
And your goal is to estimate mu. So my estimator is producing mu hat, which is an estimator for mu.
Okay.
Yeah. So it's like robust.
So it'll estimate it'll estimate the mean of the whole. Trying to estimate the mean of the original.
That's correct.
Set.
Yeah. Yeah, so this turns out to be the right statistical answer, and we can do it now very efficiently, even in the presence of outliers. Okay. And we can also do other regimes. So another regime that's been studied, which is like more restrictive than this regime, is when you have a sub-Gaussian distribution with identity covariance. And you can get the state of the right answer in terms of like the right statistical guarantee as well, also in nearly linear time. Okay. Any questions? Yeah.
Broadly speaking, do you think this regime could possibly be more generalized, or is this about what you expect about the best that we could probably hope for? In terms of like, say, but bounded covariance is one regime.
Yeah.
Do you think it's possible to generalize this?
So if there are like things you can try to do for like even more heavy-tailed distributions, but they get a little bit more complicated, I guess. In general, I think bounded covariance is a pretty mild assumption already. But it is an interesting question, I think, to generalize it further. Yeah.
Is the square root d over n rate necessary for the sub-Gaussian case as well?
Yeah. So you get some similar rate, but like this error, this root epsilon is changed, and that kind of stuff. Yeah. Okay. Cool. So now here's an outline of the rest of the talk. I'm going to describe briefly how the efficient algorithms work. Try to tell you about like this entire intuition of like this entire line of work, and then I'll try to tell you, given this intuition, why the previous algorithms are getting stuck at sort of requiring d passes over the data. Then I'll try to explain how we get around this by using these high entropy certificates and encoding this in this like matrix multiplicative weights framework, and then I'll try to put it all together at the very end. But I don't have much hope of like formally proving anything here. The hope is just to really give you the intuition of like why our approach would be able to get around these barriers. Okay. Let's get started. So how do the previous algorithms work? The whole premise of a lot of these things turns out to be the following intuition, which is that in high dimensions, it turns out that mean shifts caused by a small fraction of corrupted points can be detected in the empirical spectrum of the corrupted data set. Let me unpack that for you in pictures. So suppose the true mean of the distribution is here. I guess it's, whatever, it's close enough. This is a true mean of the distribution, but because of the red points, which you can see are sort of the outliers, and they're generally pointing in this kind of direction, the empirical mean has been kind of shifted to, say, over here. Okay? Well, how can that happen? Well, what we know is that the true covariance is bounded. In this case, the covariance of the good points is like, in this case, roughly spherical. But because the bad points are generally pushing in this direction, more than they ought to be, this is going to induce a lot of action in this shift direction, which is going to, it turns out, induce more like variance in this direction than there ought to be, which is going to cause a large eigenvalue in this direction. Right? So the shape of the data is actually going to be corrupted. It's going to be changed. It's going to be pushed out because there's going to be more points which are far out in this direction than there ought to be, because the bad points are kind of working together in this direction. So this is like the general geometric intuition behind all these things. Let me try to make formal this statement, sort of in math. So before so, I need a short definition. We say a set of samples is epsilon good for a distribution D if they sort of concentrate. So imagine S sub good is a set of good points. Okay? So then I'm going, okay, that might happen again, and so I apologize. So we're going to say that they're good if the empirical mean of the set of points, that's what this is supposed to mean, this is the empirical mean of the set of points, is close to the true mean, and the empirical covariance of the set of points is bounded. Okay, so this is supposed to be, just think of these as the original draws from the distribution before corruption. They're gonna concentrate nicely in terms of this way. This is not technically true, but just pretend it is, because it's like morally true. Okay, so think of S sub g as being the original set of good points. Okay, then sort of this fundamental lemma of efficient robust mean estimation, as I like to think of it, is the following. It takes a little bit of parsing, but I think it's relatively intuitive. Suppose that S, my corrupted set of samples, can be written as the following. S sub g union S sub bad minus S sub r. So this is the set of good points. So S sub g is assumed to be epsilon good. And what is this? This is S sub b is a set of bad points that my adversary added. And S sub r is a set of good points my adversary has removed. Okay. So yeah, S, b for bad, r for removed. That's what that's supposed to mean. And my only constraint on these two bad sets is that they're relatively small. So the size of these is, let's say, bounded by, actually, originally it should even be like epsilon or 2 epsilon times s, but let's allow some slack of like 4 times epsilon times s. Okay, then I want to say, as before, so again, the intuition was that like if the mean is shifted, then there's going to be a large eigenvalue of the empirical covariance, right? So formally, I'm going to take I'm going to take the empirical covariance of my data set, call that sigma hat, and I'm going to take lambda to be the top eigenvalue of sigma hat. Then we have the following bound, which is that the difference between the true mean and the empirical mean of my corrupted set of samples can be upper bounded by root epsilon plus root epsilon lambda. Okay, so this is sort of the contrapositive of the statement that if the mean is shifted, then the covariance is large, right? If this quantity is large, then that means lambda must also be large. Okay? And conversely, in particular, if lambda is small, then this is all at most root epsilon, which is all we could ever hope for in the first place. Okay, so this is actually kind of nice, right? Because I can't compute this distance. That's the whole point. I don't know what mu is. But I can certainly compute the top eigenvalue of the covariance. Right? Which means that now this gives me an efficient certificate to check whether or not my set of points have actually been corrupted or not. Just simply take the top eigenvalue, and if this is like a constant, then I'm happy. Does that make sense? Okay. So yeah. So this is saying that the spectra gives us an efficient certificate that the mean has been corrupted. And this has two important corollaries for us from an algorithmic perspective. The first corollary is what I just mentioned, which is that if lambda is bounded, then I can just take the empirical mean in my corrupted data set, and I know that can't be too far from the true data set, true mean. So in this case, the outliers aren't doing too bad. The second case is like in the case where lambda is large, or when this distance is actually large, because then our lemma tells us there must actually be a lambda must be large, but how can lambda possibly be large? Because if lambda is large, then that means in the direction of the top eigenvector, the bad points must be causing lambda to be large, because we know that the good points are relatively nice, right? They're nice and spherical and bounded. So in this top eigenvector direction, there's going to be much more action than there ought to be. Which means that when I project there, I'm going to find a direction where like the bad points are more noticeable than they ought to be. And so it turns out what I can simply do is just look in this direction and remove points in some meaningful way. And if I do this like sufficiently carefully, it turns out you can guarantee that you remove more bad points than good points. And I'll try to like walk through this kind of at a sketchy-ish level. But hopefully that intuition makes sense. If it doesn't, please let me know.
So this is your idea? This sounds like an older idea.
This is, turns out this appears to be new. Yeah. So, I should say, like, it turns out that like ideas like this is some sort of like leverage score sort of outlier detection kind of idea. It's been used in practice a lot, but there's been no guarantees for it. So in some sense, we're giving like provable guarantees for this simple idea. Although it turns out you have to be somewhat careful about like how you remove these points, and to my knowledge, that's never been
So
done.
you're going to sample points by leverage scores? You didn't say that.
More or less, yeah,
That's
yeah.
what you're saying now.
Turns out that's going to be one way of like doing this filtering step. Like, yeah, but I'll get to that in a second. So yeah.
Is this the approach of the 2016 papers?
Yeah, this is the earlier approach. So right now, I'm just telling you how to do anything efficiently at all. Yeah. Okay, so this is the corollary that I just mentioned, which is like what happens when the distance is actually quite large. So when the distance is quite large, bigger than root epsilon, then what it turns out is you can show that if I take v to be the top eigenvector of sigma hat, and I define these scores, which are, these are just more or less leverage scores. So tau sub I is simply the inner product of v with xi minus so this is like centering the points. I take the inner product of v and I square it. So if I define these scores, then you can show that the sum of the bad points, sum of the scores of the bad points, are like overwhelming. They're like almost 9/10 of overall sum, which means that like we have a small set of points which contribute, and notice all these are non-negative. So we have a small set of like points which contribute almost everything to the score, and this should be like extremely, red alarms. Like this looks very suspicious, and so you can use this, turns out algorithmically, to remove more bad points than good points.
So this is like turning Spielman's stop on its head, right?
Yeah, in some sense.
Okay. Right, because they do just the opposite.
Right, exactly. There's actually some, I think we don't actually use
How do
this.
you mix the two then? I mean, that's a very interesting question, right? Because I mean, everyone in sort of efficient algorithm design is throwing out things with small leverage scores, and you're throwing out things with big leverage scores.
Yeah. It's in some sense it's like the same, because we do end up with like, because it's equivalent, right? If you throw them out, that's the same as like sampling them and this kind of stuff. But in some sense, because we're in this setting where like the leverage scores are supposed to be kind of small, you can think of the inliers as being those, but oftentimes people prefer to think of the inliers as the other way around. But and here's like a brief proof of this fact, because this is already like not entirely trivial, but it should make sense. So let me just like tell you why this should work. The idea is like, okay, why am I taking these scores, these tau sub i's? Well, if I just take the sum of the tau sub i's, I'm going to get this quantity. If you just think about it for a second, because I'm going to get one copy of this and then one copy of this gives you a square. So I'm just going to do this, and then I can push these v's outside of the sum. Like this, I get this. And now this is by definition, my empirical covariance. So the whole point of like choosing these scores is I'm going to get, as the sum of all the scores, simply n times the top eigenvalue. Okay? So now I want to show that the bad points contribute almost all of the scores. Right? And an equivalent way of doing this is to show that the good points contribute almost none of the scores. Right? So I can do the same first line for the good points. I've just replaced s with s of good. And now if I could cheat slightly and pretend that I've centered properly here, if I could center here on the mean of the good points, I would properly be done and everything here would be valid. And then I could use this inequality here because I've assumed that the good points are good, meaning that their covariance is bounded by 2. And then I'd be really happy because, see, the overall sum of the points is like n times lambda, and I'm assuming lambda is really large. And this is 2. So when lambda is large, it's much bigger than 2, and I would clearly get this The problem is that I'm cheating here because I'm centering at S and not S of good. But it turns out that because of the fundamental lemma, this thingy, you can show that if this centering causes a lot of error here, it must induce way more error in lambda. And so you can relate these two quantities, and you can show that no matter what, even if this is kind of large, the overall sum of the taus must have been much, much larger. That's the general kind of sketch of the proof. So this works. And once you're done with this, once you have this lemma, then there's a randomized linear time algorithm which outputs S prime, which removes more bad points and good points. And I think Gary's already hinted at this. The idea is just simply sample in the sort of most trivial way possible. OK. And so this actually gives you a full algorithm that runs in poly time that gets the right guarantees. While the top eigenvalue is too large, compute these scores, use this linear time algorithm to remove more bad points and good points, and then keep running this, and at the end you must terminate. Because you always remove more bad points than good points. And so either you removed all the bad points at the end, in which case you're done, because now you're like happy, or you're going to output something that has good L2 norm error because lambda is going to be O of 1. So this is nice in its poly time. Unfortunately, sort of, oh yeah.
Is like the omega 1 explicit?
Yeah. It's,
otherwise, how do you implement it?
Yeah, so you can make it explicit. I'm being like a bit loose in this talk. I mean, we didn't try to optimize for this, but I think 9 works or something. I think 4 works. I forget.
No matter what n and d.
Well, I'm being like, it's like while lambda is bigger than some constant that I was too lazy to write down. Is essentially, yeah.
So it's not just like constant, like independent of n and d.
No, it is. It's like,
a literal.
Yeah, a little number. Yeah. Like this actually works quite well in practice because this is very similar to all these things that people actually do for outlier detection. The problem is that in this setting, you can prove that it actually requires like d iterations. And the high level is like what happens if the outlier puts a bunch of noise in a bunch of orthogonal directions. Right? And the issue is that we're looking for the direction of the top eigenvector. So we're only looking in one direction at a time. So what the filter is going to do, for instance, in this case, I can't pretend these are orthogonal because, yeah. I can't really draw more than, anyways. What the algorithm is going to do is going to find one direction. Good, but all the points are orthogonal. A bunch of points are orthogonal to this direction. So it's going to remove those points. But it's going to have to do this once per each time because there's d-orthogonal directions, and it's not going to find any information about the other directions when I'm looking in a single direction. Right? So this case will require d-iterations for the filter algorithm. And this seems to be sort of inherent in this case. Okay, does that make sense? Yeah.
Sorry, so you're describing why previous...
Yes, this is why previous approaches, like this filter that was in this 2016 paper, would require many iterations. Yeah. And the whole point is we're going to try to get some way of getting around this. Yeah.
But so if the points aren't in orthogonal directions, like if they're all in the same direction, then we can remove all of them.
Yeah. So if you don't put any constraints on, if you put some like structural constraints on like what the adversary is allowed to do, you can do better with this algorithm. Yeah.
So is the bad case saying that you're doing d times binary search? Like
it's d times, so each iteration of the filter algorithm requires an approximate top eigenvalue computation, so that each iteration is near linear time in the data, but you're going to need d iterations.
I see.
Yeah.
Because you're only doing one iteration.
Yeah, exactly.
So the new algorithm is going to be doing subspace.
Yeah, it's going to be doing something in...
But can you predict the data for the next iteration?
So, I mean, in this case, somehow, even if you get like all the information about like this top eigenvalue, if you're only looking in one direction, it tells you nothing about where the other points are, right? So if you're just doing one direction at a time, it's not clear. Turns out there is a way of doing this, but that's what we're going to be describing. Okay. So the idea is that the top eigenvector, it gives you some direction to look for. But more importantly, it tells you what's really important about it is it gives you a certificate that the top eigenvalue is large. Because really, recall this fundamental lemma says if the top eigenvalue is small, then we're good. Or like what we need to check is whether or not the top eigenvalue is large at all. And it is in some sense the best thing you can do. Like, the top eigenvector literally gives you the information about the top eigenvalue. But in some sense, it's really good, but we just need to be good enough. Right? In particular, all we need to do is certify whether or not the top eigenvalue is like greater than this constant, like 10. And so you can kind of relax the problem. So this is a little bit of fairly standard linear algebra. So this is, incidentally, if you're familiar with this, is just saying that spectral norm is dual to like nuclear norm. So, but I can rewrite, so a lambda is by definition the sup over L unit vectors of V transpose sigma hat V. I can rewrite this as the matrix inner product, right? These two things are literally, this is just a trace inner product between matrices of sigma and VV transpose. And I can take the convex hull of these V's to form the supremum over this set, where this set delta is a set of density matrices. So simply the set of PSD matrices over RD with trace 1. You can just say, you can just work this out for a second. And so the observation is, while this supremum is always achieved at a rank 1 vector, we don't need to find the thing that achieves the exact supremum. We can just choose any thing that it certifies that the supremum lambda is like kind of large. And this allows you to look in many directions at once. For instance, if the bad points are in m orthogonal directions, instead of taking the biggest orthogonal direction, if these directions matter, I can simply take an average of these directions. Right? And if I filter based on this sort of certificate rather than the best rank 1 certificate, it turns out that this is going to give you all the outliers all at once. So the idea is somehow we need to find a certificate that's going to find all these directions like simultaneously. Does that make sense? And the key idea is that we don't really care, again, about the form of this in some sense, so long as it certifies that the top eigenvalue is pretty large. Okay. So in general, what we want is U in the set of these density matrices, which satisfies the inner product. This is the trace inner product for just the inner product of all the entries, or the sum of the products of the entries. So such that this inner product is at least say 10, where 10 is again some relatively arbitrarily chosen constant, but relatively large. God damn. Shouldn't swear. But which is maximally diverse, right? So it's going to look in as many directions as possible. Does that make sense? And a standard way of capturing diversity amongst density matrices, if you're familiar with quantum, which I'm not, is this notion of von Neumann entropy. Okay, so it's simply, for matrix U, it's simply the negative trace of U log U. Or in other words, if U is a density matrix, it has eigenvalues which are non-negative and sum to 1. Right? So these eigenvalues form a probability distribution, and this is simply the entropy of that distribution. Right? So if your matrix is rank 1, it's going to have exactly one non-zero eigenvalue. Okay, in which case this entropy is going to be like 0. But if it's like maximally, if it's like spread out across all directions at once, then this like entropy is going to be much, much larger. And so if we maximize entropy, and it turns out this von Neumann entropy is like concave, so you can actually do this. If you maximize entropy, you're going to find a certificate which is pretty diverse. So essentially, what I've been saying so far is that you really want this. Well, you want this. You want a solution to max of the von Neumann entropy of U subject to the constraint that it is a good certificate. And then if you find this, then I can filter using the certificate, and you should find information about many directions at once. So that's why you should be able to do this using many fewer iterations. Does that make sense at a like intuitive level? Why this is like a reasonable approach? Yeah.
Yeah, I'm just looking at that comparison. So if you do the previous approach where you find the top eigenvalue,
yeah.
you essentially have to do the eigenvalue computation like several times,
yeah.
because you need to look at because you can only like look in one direction at a time. Is that the basic idea?
Yeah, that's the idea, and yeah, that's exactly the right thing. And somehow the idea is that somehow this is going to give you an efficient way of looking in all directions, kind of all at once. Yeah.
So you maximize the entropy. Is it somewhat equivalent to saying I'm picking some random directions in the condition space because the constraint is saying?
So I mean, it turns out that there is actually a closed form of this. It's actually like a matrix exponential. So it like properly reweights the directions, but it's not just taking a random direction. It's taking like many directions and combining them in some kind of specific way. Yeah.
So you could also consider like looking at a bunch of eigenvectors as a subspace, right?
Yeah, yeah.
This will give you Is there a reason this doesn't work?
So it's somehow, you want some relative scaling between the directions, right? If one direction is much bigger, that should give you more information. And so this sort of encodes that information directly. I should say it's not clear that you need to use exactly this condition. However, using this formulation will lend itself very nicely, it turns out, to fast algorithms in particular.
What I don't understand is when there's no error,
Yeah.
why don't you perturb it to the point where you get the wrong answer?
When there's no error, you're not going to find anything.
In cases when there's no error.
When there's no error, that's not going to have.
Messing around with the data, why are you going to return the right answer?
Well, when there's no error, then this is going to be infeasible because.
So I mean, I could just give you examples where there's two sets of points, a set of points far away and a set of points close in, and you're going to remove a whole bunch of these far away points.
Well,
So what's going to happen is then the average is going to move dramatically.
Wait.
I don't understand. So it must be embedded somewhere in your hypothesis that simple examples of two clusters.
Well, we're assuming that the covariance of the good distribution is bounded, right?
Yeah. So, but the simple case would be there's two clusters and you're computing the average, right?
But then I guess the good points would have pretty large covariance, right? If we're taking both of these to be good.
Yeah. So the way somehow you're saying that it doesn't apply to this case.
Yeah, it wouldn't. You would need to do
So you're saying
something.
that basically, it has to look like a nice spherical distribution.
Right. This is the setting which this works. There are algorithms that work for this other setting.
I just understand.
Yeah,
So
yeah.
the hard question is, right, is to make sure it works when there's no error.
Yeah. So when there's no error and it's like nice and spherical, and it has like bounded covariance, then this is just not going to have any solution.
So then you're just going to remove points randomly in all directions.
Well, then, like the algorithm overall that we do is first check if the top eigenvalue is like above some constant, and if it's above some constant, then do this, because then we know that there's a feasible solution,
Right.
and otherwise just terminate.
So it's going to make the data round, even if it wasn't. It's going to sort of make it isotropic.
So I mean, if there's no bad data, it would just do nothing and output the empirical mean, because it would first do this check if the empirical covariance has large eigenvalues, and if it.
So the high level is making your data isotropic, right?
Yeah, it's trying to make the data bounded covariance. Yeah. Not isotropic, because we don't know that the covariance is actually spherical, but it's supposed to make it like bounded. Yeah. Okay. So yeah, so one could actually try to analyze this directly, but that seemed like a pain to us. So it turns out you can actually embed this in a much nicer way, because it turns out that there's this framework called matrix multiplicative weights that kind of does all this for you. So this didn't make sense to me when I first read it, but apparently it's true. But matrix multiplicative weights it turns out is mirror descent on the set of density matrices with the entropy regularizer, which means that simply that doesn't have to make sense to you because it didn't make sense to me. I'll explain this anyways. But what it's supposed to be saying is that somehow it's a way of like, if I give you online versions of matrices, finding certificates for these matrices, but in a way that guarantees that these certificates always have high entropy as much as possible. Okay, so that's what it's going to be doing, and so that's exactly what we wanted. We're going to be feeding in, versions of matrices, like iterations of our algorithm, and at every time I want to find certificates for this algorithm, or for these matrices which are large, and I want these certificates to, in general, have high entropy. And it turns out that matrix multiplicative weights is going to do that for us directly. Okay, and again, I'll explain in much more detail what this means. But at a high level, the idea is it penalizes these low entropy certificates for us for free. And so instead of like dealing with all this, like actually reasoning about the structure of these high entropy certificates, we can just work with the regret guarantees that this online algorithm provides for us. And so instead of working with directly the form of those equations, we can just actually plug them into like some regret bound, and everything comes for free. Okay, and I should actually say that this matrix multiplicative weights is also at the heart of this previous algorithm by Cheng, Dieck, Nicholas. Cheng, Dieck, Nicholas Ge. It's like at the heart they reduce to these like fast packing and covering SDP solvers, which are matrix multiplicative weights. But we kind of do this kind of directly, which is I think perhaps why we avoid all these overheads. Okay, so now let me explain what matrix multiplicative weights is, more than just that sentence that Zaywon told me to write down. Okay, so let me first tell you the problem that it's supposed to be solving. So before I get to matrix multiplicative weights, let me tell you about multiplicative weights. How many people are familiar with multiplicative weights? Hopefully, okay, good. So this is the gain version of multiplicative weights, not the losses version, but it's all equivalent. But the idea is, in this setting, let's recall, the player chooses an action over, a probability distribution over d actions, and then afterwards, after committing to this action, it observes a gain vector. So it's going to get some gain based on this action, and it's going to get payout, which is the expected payout under my probability distribution that I chose. And the goal is to compete with the best action in hindsight, the best deterministic action in hindsight, which is this. So hopefully this is familiar to a number of you. Matrix multiplicative weights is just solving the natural matrix version of this, which is instead of getting a action over distributions, I get an action over density matrices. And then I also observe a matrix gain. And I get matrix payout, which is the inner product between these two matrices. And again, the goal is to compete with the best action in hindsight, but now the best action in hindsight is a matrix action. So it's just the same formulation. Okay? So how do you solve the original multiplicative weights? The original learning with experts problem? You can do the following update. So if the gains are non-negative, and if I choose the u sub t's to be given by this update, where c is a regularization parameter, which guarantees that this u has some 1, and alpha is some step size, which certifies that a null infinity bound on the f's, then I have the following regret guarantee. Okay, this should hopefully also be fairly standard for people who have seen learning with experts. It says that I compete with the best action with this sort of regret. Okay. So matrix multiplicative weights is exactly the same thing, except it's matrices. So now I have PSD matrices, and I have matrix actions given by the matrix exponential. And now C is again chosen such that things are regular. Things are on the have trace 1, and alpha has guarantees some sort of PSD bound. Then you can get the same sort of regret bound, but just replacing everything with the matrix versions of everything. Okay. So it's not super important what the exact form of this is, but you get some sort of regret bound with which you can use to analyze the guarantees of that algorithm. Okay, although I might be wrong about this, but for some reason the best reference I could find for this specific form is from 2015, which can't be right. But I asked a bunch of people, and they weren't sure either. I don't know. Maybe if somebody here actually knows the right reference, that'd be great, because this must have been known before 2015. But yeah, so now the idea is we're going to design an algorithm based on this intuition of matrix multiplicative weights forces you to have high entropy certificates, and the intuition is that must somehow converge quickly because we were looking in all these directions at once because of this intuition I was telling you before. And the way we're going to analyze the runtime of this is by using this regret guarantee instead of directly analyzing sort of what's happening with the algorithm. But the reason why this should work is because when I use these sorts of guarantees, and I'll tell you exactly how we put these things together. When we put these things when I use these u sub t somehow, I'm going to be looking in many directions at once because of this intuition that it has to be high entropy. Okay, so let me tell you how we do this. In particular, let me tell you one thing. Let me slightly simplify this expression one bit. Let me move this over here, and then when I take a supremum over all u, I just get the spectral norm of this sum. So this is equivalent to the following guarantee. Okay, but now let me tell you how to use this framework to actually instantiate it for our problem, because I haven't told you how to actually do that for actual robust mean estimation. But the idea again is that what we're going to try to use is that these updates are going to give you high, very diverse certificates. And so all we should be really doing is just taking these certificates and filtering based on these certificates. And that should just work. So we're given a set of points with large operator norm. And the claim is that after log d iterations of MMW, we're going to output a set of points where we've removed more bad points than good points, and the covariance is decreased by a constant factor. So if I do this logarithmically many times, then I'll be done. And if we want to use MMW, the only thing we get to choose are these payout matrices and my step size alpha. Okay, so I'm not going to focus on how I'm going to choose alpha, but it turns out you can set alpha to be this. The idea is that we want to design these payouts so that these u sub t's that matrix multiplicative weights gives you are going to be giving you these entropic certificates. Yeah.
So you're repeating this logarithmically many times in the operator norm of the covariance matrix?
Yeah. But it turns out you can get like a poly original bound on the operator norm of the matrix. So overall.
Yeah, so you couldn't make this arbitrarily large.
So you first can do some like very naive pre-processing to ensure that it's like at most polynomial or something like this. And then afterwards this is going to be logarithmic. So for instance, throw out points which are like clearly bad. Yeah. And before I do that, I need like a very brief tangent on these better 1D filters, which is that recall before we had this algorithm, which is that if we had sets of scores where like the bad points contributed almost everything to the sum, I can remove more bad points than good points. Turns out that if you also have a bound on the maximum of these scores, not only can you guarantee you throw out more bad points than good points, you can also guarantee that you decrease the overall sum by like a relatively large constant. And this is like also like a problem set problem that you could like give. This is very easy. So now let me just tell you how we're going to instantiate it. The idea is very simple. So how does the algorithm work? So the multiplicative weights player, which is like the certificate player, always gives us a u sub t, which is supposed to be the certificate, right? It's supposed to be this high entropy certificate. So there's two kind of possibilities. Either it's not a good like high entropy certificate, in which case, okay, we just need to wait. The certificate player just needs like a couple of rounds to catch up with what we've been doing. So let's just not do anything with our set of points in this case. Otherwise, if it is a relatively good certificate, in other words, it captures a lot of the mass of the spectral norm, we're going to filter based on this certificate, which is formally just forming this inner product, tau sub i's. Okay, this is the same sort of intuitions I had before. And use the improved filter to obtain some u set s sub t. Right? And the idea is that because this u sub t is supposed to be looking in many directions at once, this is going to give you a better set s sub t. And then now I just simply let my gain matrix be the covariance of the remaining points. Okay, and that's it. And this is, I don't think I'm going to have time for like actually giving you the analysis of this, but it's like very simple in terms of this regret. But in the intuition, which is like really what I wanted to get through, is like the reason why this will work is because we're going to be using u sub t, which is given to you by the multiplicative weights framework, which is going to find you many directions all at once. That's the idea. Okay. So let me try in like the 10 minutes remaining to give you a very high level sketch of like why this should work. So again, recall that we had this definition of epsilon good, which is that the good point, the mean is converging and the covariance has bounded covariance. We're going to assume again that we have the structure where like S is mostly S sub good and we have this S sub bad and S sub r, which are both relatively small. Okay. Then we have the following linear algebraic fact, which is that if I have S prime, which is like a large subset of S, then there's some relationship between the covariances, just because I haven't removed too many points. It can't be 2 PSD less than anything else. And then we have the following crucial lemma, which is that in the case where my certificate is actually certifying a relatively good bound on my covariance, then we throw more bad points than good points, and we decrease the sum, this inner product, by a fourth. But if you like parse this is just really saying that the improved filter works in this case. Okay, so to verify this lemma, all we need to show is that the improved filter, that the conditions of the improved filter are satisfied. And the improved filter just required that the bad points contribute like 9/10 of the score, and the good points contribute almost nothing. Okay? So if we have these two things, then it's like very easy to actually just plug them into this regret bound, and you're going to get the bound that we want. Okay, so this is exactly the regret bound I had before for generic multiplicative weights. I'm going to instantiate this now with our choice of alpha and these lemmas. So this is just instantiating my choice of alpha, which was like 2 over the covariance or something. Yeah, and you get this bound. And now I'm going to plug in this lemma to try to control things. So how do I do this? Oh, yes. Forgot. OK. So this is just replacing this term with this bound. Ah, there you go. Well, I should mention that this inequality here, which I'm going to be using, just follows because of the first fact up to like epsilons. This is just saying that like this. So this can be upper bounded by the spectral norm of the covariance of S sub t minus 1, right? Because this is interpolated with something on which is the density matrix, and you can show that this is related to the covariance of the original set because I haven't removed too many points. Hey, I should say it's not too important to like follow this analysis as long as you got some sort of intuition about like why it's true.
Don't you lose something going between the second term and the last term?
Yeah, I think you might lose like a 1 minus epsilon. So this might be a typo. Yeah. But yeah, so once you have this inequality, I'm just going to plug this into here to replace this, and then when you simplify things, you get this expression. You just stare at it for a second, because you get t of these, and yeah. And so now I have this bound on the covariance of the sum of the covariances, and I'm just going to use the following simple lower bound, which is that because I have this PSD ordering constraint on my matrices, because I haven't removed too many points, the covariance of the sum of the covariances, the operator norm of this, has to be at least the t times the covariance of the smallest thing, because they're all, you think of them as like nested ellipses, and I'm summing them. So the largest direction of the smallest thing must be represented t times. So I have this up to this smudge of 1 minus epsilon because I have these 1 minus epsilons everywhere. And so when I just like put these two things together and divide by t, I get this. And so now you just observe this is some small constant if epsilon is not too small. And this is, or sorry, too close to 1. And this is also going to be some small constant so long as t is like roughly log d. And so overall, I'm going to make progress. Okay. And that's the entire, yeah.
So can you give some intuition? I mean, the algebra is nice and fine, but what's happening here? Why is doing the right thing?
So yeah, so the idea is that the reason why you should expect this is again because MMW penalizes low entropy solutions. So this u sub t that I'm finding must be a high entropy certificate for the fact that the covariance is large spectral norm. And so when that's happening, you really have to be like removing all directions at once. And when you do that, the spectral norm has to decrease because I'm going to be finding all directions which are large simultaneously. Frankly, that's all the intuition I have as well. So.
Why does it penalize the low entropy ones?
Oh, that's just by the way it works. Like, so what you can think of is that what matrix multiplicative weights is doing, it is like a first order update method, and it literally has a regularization term for like low entropy. So it's going to favor high entropy certificates to low entropy certificates, just like if you write it out as a first order mirror descent method. So when it's doing that, then you should expect that you're going to find.
On the other hand, it also has to conform to the
yeah. So it's going to find.
You're giving, right?
Yeah, but the parameter I'm giving is that it finds something that, like my constraint is that it is finding a direction where the covariance is large. But that's the only constraint that I'm giving. So it's finding some direction where the covariance is large, or some matrix in which the covariance is large that has high entropy. And that's the whole idea, yeah.
So these payoff functions of these various covariance matrices,
Yeah.
they always have a direction in which they are common.
Yeah. And that's
so you have to respect that.
Exactly, yeah. And somehow it's like.
It's not a direction, but a set of directions.
Yeah.
So in the case that the bad case for the original algorithm where you have d directions that are orthogonal, equally spreading epsilon over d times that of the points, the bad points in each of those directions. So that what this is going to do is it's going to find a direction that's like basically a linear combination of all the directions, right?
Yeah.
Probably roughly equally.
Yeah.
So in that setting, would the leverage scores of all the bad points, wouldn't they be cut like a d factor?
Yeah. So the leverage scores would be, in that case, would be good. Like just the usual leverage scores would be, I think, good enough. But somehow.
But the leverage scores of the bad points wouldn't get cut down a substantial fraction enough for would they still be as a constant factor of the total leverage score weight? Because the worry is now you've taken some sort of combination of all of them, and now that the bad points don't sound out as much.
So somehow the idea is that like because they're in orthogonal directions, if I want them to be like affecting the mean, they each further have to be like further out, right?
Okay.
Because there's fewer of them.
That makes sense.
Yeah. And it turns out that it just works.
Yeah, that makes sense.
the IDOB Impala paper, they explicitly use that the bottom half of
Yeah.
the empirical covariance is good.
Yeah, that's right.
And this is now like explicitly searching over, say, in the top half.
Right. Well, it's not searching for a specific half. It's searching for like a specific kind of set of directions, like a convex combination of directions, which is perhaps why it's like better. Right. It's sort of like adaptive. Okay. And I don't really want to get into the sketch of the lemma, but it really is the same as before, just because if I'm having a direction with large variance, which you should think of as use of t, the good points can't contribute anything. It must be the bad points contributing almost everything. It's like the same computation as before. Like this is all stuff that you had seen before, just with use of t's instead of v's. And you can just use, again, the fundamental lemma to always show that the good points contribute almost nothing. But this should hopefully be believable, if like even if it's like not followed. Okay, and now there's just like one kind of minor catch, sort of, which is that this algorithm is like not actually fast, as written. Just because even writing a density matrix out generally, well, a density matrix is d by d, so you would need d squared time to just write out a general density matrix. So you can't actually do this as written. Like, how do I compute these scores that I wrote? It's not obvious. But it turns out that there's a relatively standard toolkit for kind of solving these problems very efficiently using like sketching and dimension reduction and this kind of stuff. And the key point is that somehow we only really need very crude approximations to these scores, because what we're looking for is this like constant gap, that the good points contribute like almost nothing and the bad points contribute like 10 times as much. So even if we have like 2 approximations or like 4 approximations or whatever, like, or yeah, whatever, root 10 approximations, it's good enough for us. And so we can just use like very crude approximations, and you can do this using like these fast numerical linear algebra kind of ideas. Very briefly, because this is only going to be interesting for like some of the experts. You can first observe that this is like the L2 norm squared of some vector, which is u t to the 1/2 times some vector squared. And to compute L2 norms of vectors, you can use JL to do it efficiently. So if you take a JL matrix, you can dimension reduce this problem. The problem is that this use of t is already like some matrix exponential, right? It's this matrix exponential kind of thing. It's not even obvious to do this. So we need to somehow compute this matrix R u t to the 1/2 very efficiently. And for this, turns out you can just do some polynomial approximation kind of tricks. So you can approximate the matrix exponential very well by a relatively low degree polynomial. Again, it's not super important if you don't follow this part. And I can compute like JL matrix times this polynomial very efficiently. So you can compute this matrix very efficiently, and now then I'm very happy. Again, not super important if you didn't follow this part. But then that's it. What you do is you do the same thing and you do this slightly more complicated looking set of scores, but it's really the same idea as before, just to make it fast. And then you're done. Yeah.
When you apply your matrix multiplicative rate update, are you applying it to the entire U matrix or like the sketched U matrix?
So you first compute this sketch matrix and then you apply this like much smaller matrix to every vector to make it run in nearly linear time. If you didn't follow it, don't worry, I guess. But there's a standard toolkit. That's the main point for doing these sorts of tricks very fast. And that's it. Okay, so that's more or less it. So some very interesting, and yeah, again, the intuition that I'm hoping that hopefully makes sense is that this matrix multiplicative weights finds these high entropy certificates for you for free, and this is what we really wanted all along. We wanted to find all these directions simultaneously. And if we just go through the MMW framework, we just get that automatically. That's sort of like a one-line kind of thing. So some open questions. A very interesting question I'm kind of working on a lot right now is like, how well does this perform in practice? I don't think this whole MMW stuff is going to be very nice, but if you like kind of simplify this, to just take high entropy certificates in general, this seems to be working very well actually in practice. Another question is like, can we use these ideas to speed up other robust estimation tasks as well? Okay, that's pretty much it. Thanks. Sorry, say again?
Doing regression instead of median.
So regression turns out is like one of these problems that you can like kind of black box reduce. like robust regression is oftentimes you can like black box reduce it. Like I think Siva has a paper about this, where if you just like estimate the mean of the gradients robustly, then you can do SGD, but with a little bit of noise. And then so you can do, so that then you can also just run every iteration very efficiently. There's still some stuff that needs to be worked out to get like truly linear time algorithms, I think, for that, but you can do something already with this that's faster than previous algorithms. Does that make sense? Yeah.
Yeah, so knowledge of covariance is still, upper bound and covariance is still required. Right?
Yeah. So yeah, one thing I should mention is that, okay, I guess I should say I'm like 90% sure that you need to know at least the covariance or epsilon. So this algorithm requires you to know sigma. You can actually work out, you don't need to know epsilon for this algorithm to work, which is, I think, important in practice.
What is epsilon?
Oh, epsilon is a fraction of corrupted data. So this algorithm, it turns out you actually don't need to know epsilon because this filter that we're using doesn't need to know epsilon, and our termination condition is stop when the covariance is 9. But I think you need to know at least one of sigma or epsilon, otherwise the problem in some information theoretic sense is impossible. And if you know epsilon, you can do some other tricks but not sigma, you can also do other tricks.
So for bounded second moments.
Yeah, for bounded second moments, that's right. I think so maybe not.
So for like the Lie-Down would not work for bounded second moments because they didn't assume knowledge of.
No, they assume an upper bound on the covariance. Wait, but I thought that, I'm pretty sure their termination condition is like top eigenvalue is at bounded by like O of sigma, right?
No, it's a recursive algorithm, right? So
but like the recursion stops when the top eigenvalue that they find is small, no?
When you hit one dimension.
Oh, really? Oh, okay. Okay, yeah.
Just to be sure, what exactly do you need to know about the distribution in order, or like what information do you actually need to be able to run this? So like, you need the so like do you like are you assuming that the underlying data follows like this covariance matrix? Like, is that the sort of thing?
Yeah. So you need that the original distribution before corruption had bounded second moment.
Do you actually need the covariance matrix itself? Like,
No.
So you're just making the assumption that
Yeah,
it's second moment.
And why is that true in regression?
Well, if you make typically the assumption, or one of the many assumptions in regression is that like the variance of the gradients is bounded. So since we're applying mean estimation to the gradients, that's what we need. Does that make sense? And typically, actually, in regression, they often assume a stronger thing, which is that the variance of the L2 norms of the gradients, or like the expectation of the L2 norm of the gradients minus the true gradients is bounded. That's like an even stronger assumption. Yeah.
So what question is related to this distribution question? If I view this more as not as a distribution problem, but some adversarial or some fixed data, but it's corrupted with adversarial noise.
Yeah.
Then are we really using the covariance of the distribution, or just
the
covariance is enough?
Yeah, just the sample covariance is enough. Yeah, because again, all the analysis, it turns out, works under the epsilon goodness condition, which just assumes that the empirical mean of the good points is converging to something, and the empirical covariance is bounded by 2, or some constant. Yeah. Okay.
If there are no more questions, we can thank Jerry.